things. I sent out a little announcement. We are also vote for Red Monkey. That was one of the places I went on my 21st birthday. Okay, that's another good one. Okay, science. We are getting to about the halfway point for this badge. I haven't updated the scores yet. I'll try to do that tomorrow. But I am going to highly encourage you to check out some of the labs this weekend or think about maybe doing a homework project. I sent out a few podcasts I like, but there's just a ton. Since this semester, this badge, we have both galaxies in the universe and also aliens, dark matter, and NASA missions. There's a just bunch of stuff out there that you could relate to what we are studying right now. So I gave a few suggestions for homework projects. The 4 labs that are based on the universe are all available. So there's the Milky Way lab where you can replicate the work that won the Nobel Prize this year. So that's really cool. There's the Galaxy lab where you can measure the rotation of a galaxy and also look at how we use supernova to measure distances. There's the Age of the Universe lab, which we're going to talk a little bit more about today, sort of, but lets you measure the age of the universe using redshifted galaxies. And then there's the accelerating or the expanding universe balloon lab, where you use a balloon to model the expanding universe. So I'd highly encourage you to try to do 1 or 2 of those over this weekend, or at least start thinking about those to get those badge points. Since we are coming into the edge of the semester, and I don't want to be piling on everything for you. So if you can do them now, you don't have to do them while you're working on all of your final stuff. Any questions about that? And always feel free to email me. If there are topics that you're interested in, but you're not finding stuff, shoot me an email. I might know of something that I can point you towards. But today we're going to kind of finish up talking about galaxy evolution and the universe. You're going to be able to do some more work to earn a Nobel Prize. So you can, even if you don't do that lab, you'll be doing some Nobel Prize winning work in class today. But I wanted to start out just with a reminder of what we ended with last class. So last class, we were looking at the Hubble Deep Field to see how we could use galaxies at different redshifts, so different distances away from us, to predict to see how galaxies look like they were changing over time. So this is what you guys were looking at, and you were looking at the differences between the nearby galaxies and the really high redshift galaxies to see if you could see differences in structure, shape, size, color, that kind of stuff. Just to show you how cool this is, so this is, this is the Hubble Deep Field that you looked at. In order to get this image, Hubble looked at a pretty much blank area in the sky. So if we were to look at it with our eyes, we wouldn't see anything, but Hubble looked at it for 10 days. So took pictures for exposure times of 10 days. And it's a size of the sky. This is comparing that size to the moon. So down here, this little box, is showing the size of the sky in comparison to the full moon. So it looked at a little area of the sky and found 3,000 galaxies. So just a really awesome data set for us to get this picture of galaxy evolution by looking at more and more distant galaxies. So the more distant a galaxy is, the longer it took its light to reach us, which means that galaxy is younger. So we're seeing it earlier in the history of the universe, making it younger. Today we're going to think about a few other ways we can determine the history of the universe and what we know about how galaxies evolve. So one way we can do this is by looking at stars. If we look towards the center of our galaxy, we've been able to find a few stars that seem to have formed around the same time as the Milky Way formed. So this is one of those stars, HD 140283. And the way we identify these really old stars is by looking for stars that have little to no iron, so none of those heavy elements. And the reason why they wouldn't have any heavy elements is if we think back to when we did the "You Are Made of Star Stuff" activity. We need massive stars to live and die in order to get iron and these heavy elements. So if a star forms before any of those massive stars died, there's no iron in the universe for them to form out of. So we don't expect some of the earliest stars to have any heavy elements. We expect them to be pretty much all hydrogen and helium. So if we can find stars and look at their spectra and notice that they don't have any heavy elements, then we can predict that some of these must be the earliest stars formed. And it just gives us an idea of maybe what these early stars look like, how they might have been different, and also where they are in our galaxy might tell us a little bit about how our galaxy has been growing over time. So most of the ones we found seem to be towards the center, and some of them, the oldest stars we found seem to have formed about 300 million years after the Big Bang. So that also gives us some idea about when the Milky Way was forming too. We can also use stars to measure how the Milky Way has grown over time, specifically by looking for signs of galactic cannibalism. So galactic cannibalism is when a large galaxy consumes a smaller one, so eats a smaller galaxy. This allows for the larger galaxy to grow and form new stars, because all of a sudden there's a bunch of new gas and material for that galaxy to form stars out of. This won't destroy a galaxy, it won't mess with its structure because the dwarf galaxy it's eating is usually pretty small. So it's just adding material, making the galaxy bigger. And by looking around the Milky Way, we're able to do something called galactic archaeology, where we can kind of build a picture of how the Milky Way has been growing over time by looking for these streams of stars that seem to be the paths of dwarf galaxies that the Milky Way ate in the past. So this image down here is showing the Sagittarius stream, where there was a dwarf galaxy called the Sagittarius dwarf that is slowly being pulled apart and sucked into the Milky Way in this act of galactic cannibalism. So measuring these different streams allows us to do galactic archaeology and build a picture of how the Milky Way has grown over time. We can also see these kind of minor merger events, these acts of galactic cannibalism in other galaxies, and use what happens by looking at those galaxies. Look to see what's going on to kind of see how eating a little galaxy allows a bigger galaxy to grow and form new stars. So that's looking at stars, either looking for really, really old stars or by looking for kind of these streams of stars that tell us about the history of our own galaxy. We can start to build a picture of how the Milky Way has grown over time and also how other galaxies might do similar things to grow over time. Besides besides eating little galaxies, big galaxies can also clash together. So I'm gonna play this video and kind of keep talking at the same time. So this video is going to show a simulation of two galaxies colliding and compare it to some images we have of colliding galaxies. It's pretty incredible how great the simulation is. But what we realize based on computer models is that if you take two spinning disks and you slam them together at kind of opposite rotation angles, you end up losing that nice organized motion and end up with just a lot of kind of random motion and probably a blob of stars and gas. So when we take two disk galaxies and mush them together, you often end up with an elliptical galaxy. So this is one way we might end up, why we see spirals and ellipticals, is maybe spirals are galaxies that have never collided with a galaxy of the same size, whereas ellipticals are galaxies that have gone through a lot of collision events in their past. And this is just, yeah, that video this is one of my favorite ones to show. It's just so cool how we're able to see this and compare our models, which seem to have some pretty good real world, real universe, I guess I should say, counterparts. And as they smush together, we're losing that structure, but we are getting large amounts of new stars forming because the gas from the two galaxies is mixing up, creating new stars, although it's unlikely that any of the individual stars in the two galaxies will collide. And I think I did mention this, but this is something that's eventually going to happen to the Milky Way. We don't think the Milky Way is still a disk, so we don't think it's gone through any major mergers in its past, but we can see that the Andromeda galaxy, our nearest neighbor galaxy, is moving towards us, and we think after that collision, we will probably be an elliptical galaxy. So instead of seeing a nice bar of stars in the Milky Way across our sky, we'll see one giant clump of old stars. But this will be in 5 billion years, so long time from now. By using our method of looking at more and more distant galaxies, we can also get why is Andromeda moving toward? Great question. So that's really just gravity. So Andromeda is close enough to us that the gravitational pull of the Milky Way is, and Andromeda's pulled towards, so we're moving towards Andromeda, Andromeda's moving towards us. So they're just being gravitationally pulled together. If galaxies are close enough, the gravitational pull will be greater than the expansion rate of the universe, so they can actually get smashed together even though the universe is expanding. So yeah, it's just gravity. The nice thing in astronomy, one of the main forces we worry about is gravity. So pretty much everything we see holds together. Back. Okay. Sorry, jumping back in. So by looking further back in time, we've been able to notice that at around a redshift of 2, or at a location about 10 billion light years away, so 10 billion years in the past, there seems to be a lot of galaxies undergoing these merging events. So at around a redshift of 2, these are a bunch of galaxies that we're looking at around a redshift of 2. And we can see that a lot of them seem to have multiple bright spots. So it's not just one galaxy, it's, at least 2 galaxies merging like in this one, but in this one here, it looks like there's maybe up to 5 galaxies merging together in this image. So maybe something's going on around a redshift of 2 where a lot of galaxies are going through these big collision events, and either if they are going through a collision event, they're turning into an elliptical. And if they are not in a location where there are other galaxies for them to collide with, they're staying as a spiral. So this is kind of one of our big theories about why we see ellipticals and spirals and why they look so different. Another really cool thing, there's something called the cosmic star formation rate history, which tells us how galaxies have formed stars over time. And we've noticed that there's a peak in this. So galaxies are forming the most stars that we see ever at this redshift of 2. So about 10 billion years ago, galaxies are crazy forming stars. And then since then, it's kind of dropped off. So potentially these collisions were forming ellipticals, they're going through this huge burst of star formation, and then they're running out of material to form new stars, and they stop and become red and dead galaxies. Any other questions there? So we have galactic cannibalism, and we have galactic collisions. And the big difference between those two things is cannibalism is when we have one really big galaxy and one really small galaxy. Collisions are when the 2 galaxies are about the same size. Okay. Collisions can also cause the galaxy to turn on an active galactic nuclei. So if you've ever heard the term quasar, this is what a quasar is. It's a galaxy with an active nuclei. So the nucleus is just the center part, and being active just means that it's outputting a lot of light. So as the 2 galaxies collide or after the collision, material from the 2 galaxies might start to fall onto the central supermassive black hole. And as it falls onto the central supermassive black hole, it will move incredibly, incredibly fast. So 500 to 5,000 kilometers per second, which corresponds with 1 times 10 to the 7th to 11 times 10 to the 7th miles per hour. And this really fast moving material just creates these huge bursts of luminosity, these really bright centers of these galaxies. So we can see them from really, really far away. They also might produce these radio jets, so that's what this is showing here. So material that's getting shot off, so stuff can fall in, but it's also possible that some of it ends up blowing off. And that creates these just incredibly energetic radio emission jets from these galaxies, which again, we can observe from really far away. So AGNs are both something that could happen as a galaxy evolves, but they're also a way for us to measure really distant galaxies because they are just so screamingly bright that we can see them even if they are really far away. Based on these measurements of galaxies, we can start to determine also the structure of the universe. So by mapping a lot of galaxies, finding where they are and how they are positioned throughout the universe, we can kind of create a map of how galaxies are aligned. So this thing that's moving around, this GIF over here, is the map that was made by the Sloan Digital Sky Survey. So if any of you have done the Galaxy Zoo citizen science project, that is using Sloan data, but they are just able to create this pretty incredible 3D map of the location of every galaxy they've imaged, both in terms of where it is on the sky and also how far away it is from us. And we see that it's pretty similar in every direction, but there's kind of these clumps of galaxies that form together, separated by these big empty areas. Now, you'll also notice that there's kind of these two big areas where there's no data. That's not because there are no galaxies there. Does anyone have an idea why maybe could we not see any galaxies? What would prevent us from seeing galaxies in this kind of band around us? Any thoughts? I've got the chat open if you have an idea what that could be. Yep, exactly. So that's where the Milky Way, our own galaxy, blocks the light from other galaxies. So we can't see the galaxies that are in the plane of the Milky Way. So we can create a map and we have to kind of assume that it would be the same if we could see through there, which there's no reason to think it wouldn't be, but we still get this really incredible maps of the universe. And what we've noticed from those is that galaxies tend to form in clusters with giant empty spaces called voids between them. So groups of galaxies join together to form larger structures called clusters or superclusters. These can have hundreds to thousands of galaxies in them. The Milky Way is technically kind of on the edge of the Virgo supercluster. So the Virgo supercluster shown here. We're not quite in it. We're in something called the local group, which is smaller. It's only about 38 galaxies, most of which are really small. So there's only 3 big galaxies in our local group. The other thing that astronomers have noticed is that most giant elliptical galaxies tend to be found in the center of really big superclusters. And that's important because that tells us that it makes sense that merging galaxies will form ellipticals, because then we would expect them to be where there are a lot of galaxies. So the fact that we see ellipticals in the center of these clusters is a good sign that we get ellipticals from merging. You need to have a lot of galaxies in order for galaxies to collide, so we see the most results of those collisions in the center of big groups of galaxies. Kind of on the flip side, we see spirals in more isolated environments, so we see spirals more often kind of by themselves, like how the Milky Way is in this small group of 38 galaxies instead of in a larger cluster of hundreds to thousands of galaxies. So this all just again supports that the reason we see spirals and ellipticals is that the way we get ellipticals is by slamming together at least 2 spirals. The voids between the galaxies seem to be pretty dang empty. We don't know a lot about what's going on here since we can't send anything to one, but there doesn't seem to be much gas, dust, anything else. Superclusters have some gas between the galaxies, but these voids just seem to be pretty empty. So there's a lot of our universe that is just empty space, which is kind of spooky to think about. To understand, so still kind of focusing, so kind of, let me go back here. Any questions about large scale structure of the universe? clusters and voids. Okay. So another way we can kind of try to understand how galaxies grow and evolve is by using computer models. So this one here is from something called the FIRE simulation. So we're showing time, redshift up here, so age of the universe, and they're just showing a galaxy growing over time. And what we're really seeing is that first of all, these models are incredible, but the computer simulations kind of we put in a certain amount of matter, we say there's this much stuff in the universe, and then we tell the computer, this is how that stuff interacts, and what's going to happen if it's allowed to interact for just billions and billions of years. And we do see some structures forming that look kind of like galaxies, so that's good. We see some merging events and some kind of large outflows. So there's some maybe little dwarf galaxies that this bigger galaxy that this simulation is looking at is eating. I don't think this one goes through a major merger, but we can see over time just different things happening, it being fueled for star formation. There's definitely some disk structure that looks like it's forming here. So these computer models are a really nice way for us to kind of test our theories about how the universe forms and how galaxies evolve and see if it makes sense with what we know about how physics in the universe works. So this is another question. What do you guys think? What might be one of the most important forces that astronomers need to consider when they make these computer models? So what physics goes into these models? Oh, there's a major merger. Ooh. Yeah, so the main thing is that we need to model gravity. So the earliest models really only had gravity. Now we can model a lot of other things too. We can think about gas pressure. We can think about star formation, what's going to happen after stars form. There'll be supernova. Supernova explosions can actually clear a galaxy of the fuel needed to form new stars. So how that might happen. But the big thing is we need to know if you have a bunch of particles of mass and you put them near each other, how is the force of gravity going to pull them together? So that's what a lot of these models do, is that we say there's this many particles of matter, dark matter, gas, and they interact through gravity and through pressure in these ways. What's going to happen if we run time forward? But based on those models, we do get these same kind of, this image here is a model showing how we think large-scale structure should grow. So a computer simulation made this image, and it matches pretty well with our observations of large-scale structure. So our models of gravity are seem to match pretty well with what we see with large-scale structure. And our models of gravity of galaxies merging together do show disks becoming ellipticals, and they do pretty well reproduce a lot of the collision products that we see in galaxies around our universe. So computer simulations are pretty incredible ways for us to figure out how the universe grows over time. So from all of this, we have a few theories about how galaxies form, and they're kind of vaguely, we're going to split them into bottom up and top down. So bottom up structure formation means we start with a lot of little galaxies that are going to merge and grow together to form bigger galaxies. And we think this one is probably pretty true. It seems to be with what we see with mergers, with what we see with galactic cannibalism. It seems like in the beginning of the universe, there are a lot of these smaller galaxies, and then over time, some of those have grown and formed bigger galaxies. Top down would be kind of the opposite. We start with one big kind of pancake of matter that slowly splits apart to form smaller and smaller individual galaxies. This doesn't seem to quite match our data, but there's probably some amount of kind of an in-between that is actually right. So it's probably neither exactly bottom up or top down, but something slightly between these two, where we're both getting smaller things merging, but also potentially having bigger things breaking apart. There are some other factors that could go into how galaxies form and what galaxies look like besides these just big merging events. For example, when initial galaxies start to form, so you start with a big clump of gas and dark matter, so the protogalactic cloud. Depending on the conditions in that protogalactic cloud, you might end up with an elliptical or a spiral just because of how physics works. So back to kind of thinking about pizza, we can think if you have a ball of pizza dough and you spin it around, that's how they make it really flat. The same thing kind of happens with galaxies forming. So you have your big cloud of gas and dark matter. If it's rotating, it's going to get flat. If it's not really rotating, it might stay round. So that might mean that some of the spirals we see are just galaxies that when they were forming, they were also kind of had some amount of rotation going on that turned them into a disk. Whereas ellipticals didn't have that nice rotation, so they stayed kind of more blob-like. Another thing that's important that could matter is that really dense cloud of gas would be able to form stars faster and then also cool faster, so use up its fuel to form stars really fast. So if your protogalactic cloud of gas and dark matter was really, really dense, maybe you don't have sustained star formation and you turn into a red and dead elliptical. Whereas if it's lower density, you're not able to form stars as efficiently, so you end up with a sustained source of fuel to form new stars, so you end up turning into a blue and new spiral. So some theories about ellipticals is that maybe sometime in the distant past they were forming a lot of stars, but since then they have run out of fuel, so now they're not forming any new stars, which makes them red. So possibly you could get that without a merger if you're just a really big high density cloud of gas, dust, and dark matter. So just kind of in conclusion on what we know about galaxy evolution, is that there's still a lot we don't know is kind of the first thing. But based on using our telescopes as time machines, we can make these kind of evolutionary pictures of what galaxies have looked like at different times. From that, we see that merging galaxies seem to be really important for what determines whether a galaxy is going to become a spiral or become an elliptical in the present day. We can also use computer models to see that mergers could create giant elliptical galaxies. And by looking at the location of galaxies, that we see more ellipticals in these clusters and more in the center of superclusters, whereas more spirals tend to be at the edges or kind of in the connecting areas between superclusters. That also supports this theory that merging seems to play an important role in galactic evolution. So just before we start thinking about the Big Bang and the timeline of the universe, just kind of as a review, we started our discussion of galaxies in the universe by looking at our galaxy, the Milky Way. We then talked about the two different classes, spirals and ellipticals. Since then, we thought about why we might see those classes and what kind of interactions galaxies can go through that could cause them to grow and evolve over time. Any questions here before we switch subjects a little bit? So the last thing to think about now in this badge before we get to our student choice section is to think about the Big Bang and the beginning, the history of our universe, the future of our universe, what's going to happen, where we are, why is everything expanding, what's going on. So these are some of the big, more cosmological questions we can try to address as astronomers. First, though, we should think about what the universe even is. So one of my biggest pet peeves is when people say there are more blanks than there are stars in the universe, because I don't think we know how many stars there are in the universe. But that's a little thing that I get annoyed about. You can say there are more grains of sand than there are stars in the observable universe. I am fine with that. That is finite. But the universe itself might actually be infinite. We don't know if the universe has an edge. So there's a possibility there are an infinite number of stars in our universe. I don't think there are an infinite number of grains of sand on the beach. So yeah, I don't like it. That's a little thing that I get annoyed about. But anyways, the universe is kind of everything that we see around us. So does it have an edge? We don't know. Does it go on forever? We don't know. But we do know that we can only see things that are about 13.7 billion light years away. And that's because light takes time to travel to us, which is why we could use telescopes as time machines. And the universe is about 13.7 billion years old. So something emitting light that is 14 billion light years away, the light that is emitted does not have time to have reached us yet. So in the entire history of the universe, that light wouldn't be able to get to us. So 13.7, we've got this kind of bubble around us that is the observable universe, which is everything we can see. It's a bubble with a radius of 13.7-ish billion light years. Beyond that, anything that there could be stuff there, I'm not saying there is not stuff there, there very well could be, but the light it is emitting has not had time to reach us because the universe hasn't existed for long enough for that light to reach us. So if that doesn't hurt your brain, but I don't know. But this is just kind of, the universe is kind of everything that we see around us, potentially infinite, going on forever, but that we don't actually know. We think, as I said, we think the age of the universe is about 13.77 billion years. If you want to measure this for yourself, there is that Age of the Universe lab that you can do that for. We look at the way we find the age of the universe is by looking at the Hubble expansion rate and kind of backing out to when the universe would have been, when everything would have been in the same spot. So just like if we think about when we measured the age of the Crab Nebula, we looked at how fast it was expanding to find out when everything in it must have been one small star. We can kind of do the same thing with the universe. Everything in the universe is expanding. We can kind of trace that back to figure out when every galaxy in the universe was in the same teensy tiny spot. And that tells us how long the universe has been expanding, which gives us an age of the universe. The problem is this assumes that the universe has been expanding at the same rate for all of history, all of universal history, which is not quite true. The rate of expansion depends on how much of different types of things are in the universe. So how much matter there is, how much dark matter there is, how much dark energy there is. So really good models take into account that the expansion rate of the universe has changed over time to get this 13.77 billion number. So when you do this lab, we're just going to assume that the universe has been expanding at the same rate over time, which makes things a little bit easier, but your number won't be quite right, but it'll be really close. So that's cool. As I said though, the universe is not expanding at a constant rate. And one thing that we've noticed is that it seems the rate the universe is expanding seems to be accelerating. So the expansion seems to be getting faster and faster. And this is where you guys all have the opportunity to earn a Nobel Prize. So our activity for today is this day 18 activity. So day 18, the Big Bang. You can't tell, I really like this activity. It's gonna be a little tricky to do in a computer, but I think I found a way to do it. So this is similar to normal. There's a quiz. We're gonna be doing some plotting. The problem is I need you to do this plot on a really specific graph. So there's a few ways to do this. There's a PDF. If you have something where you can draw on a PDF, you can download this PDF and draw on it. I need you to add the supernova measurements to this graph so we can compare them to these 3 lines. That's why we can't just do it in an Excel spreadsheet. The other option is I've given you a Google sheet that is going to be view only, but if you go to File and you say make a copy, that will make a copy that you can edit. So make a copy in your Google Drive. And then you can add your own supernova to it. So I think it's easier if you add some lines just by inserting a few lines. You can add some lines and you can say, you can figure out, so let's say for the second supernova, it's at a redshift of 0.026. So I want to move my line, so this is 0.01, 0.02, so about 0.026 is going to be somewhere in here. And it has a distance modulus of 35.76. So I can move this up to, so 35.76 is going to be around here. So that means I would want to put a point representing one supernova right on the center of that line. So I don't need you to add every supernova, there's a bunch of them, but I want you to definitely get these higher redshift ones, so especially these last 3 on here. So try to get at least 5 or 10 of these supernova onto that graph. It's a little tricky. Normally we would just draw. I can't send you this material, so we're going to have to kind of use this Google or PDF. And you're going to use that to figure out how the expansion rate of the universe is changing over time. So I'm going to open up some breakout rooms. As I do, does anyone have any questions, concerns, comments? Okie doke. Rooms are open. Let's work on this till around 12:30.